Hi, let's dive into lesson 6 handout on the Minimax algorithm. So our first problem asks us to find the optimal path using the Minimax algorithm. The up arrows are maximizing agents and the down arrows are minimizing agents, our adversary, who wants to pick the lowest reward value, point value for us. So what we're gonna do is percolate these leaf nodes up, the end state of all the possible branches of decisions. We're going to percolate those rewards up by selecting the minimum between two decisions, because the adversary has kind of the last say, the last action in this game. So the minimum between 5 and 2 is 2. Here we have, actually I'm gonna copy this into every box so we can quickly allocate them. Okay, the minimum between 9 and 13 is 9, -4 and 10, -4. Here is 1, 4, -7, -9, and -2. Now we're going to percolate these nodes up to a maximizing agent layer. So the up arrows represent picking the largest values that are possible. They kind of represent us, the player, and we want the most points. So -2, -9, 9 is higher. -4 and 1 is higher. 4 is higher, and -2 is higher. Now we're gonna percolate this layer up to a minimizing layer. And this is like a turn-based game where I make a move, enemy makes a move, I make a move, enemy makes a move, and this is the final game state. Just to clarify, so minimizing layer, we have a 1 is less than 9, and then we have a -2 is less than 4. And finally, we make the first move in the game, and we're gonna go down the branch that results in the highest number of points, which is 1. All right, number 2. So similar thing, except this time it's asking us to determine what values of X of this leaf node right here is guaranteed to choose, is player 1 guaranteed to choose action 1 for their first move. So in other words, as long as action 1 has a higher cost, right? Player 1 is maximizing agent. As long as action 1 has a higher number of points than action 2, then we're gonna go down the left branch. Let's solve for X. So we will first find action 2, which is a little easier because we know all the leaf nodes. Let's go CS471. Got some loud freshmen. Okay, so just so I'm not skipping steps, we're selecting the maximum between here, and then we're selecting the minimum between here. So already we know, as long as action 1 is more than 8, let's insert, as long as action 1 is more than 8, then our agent, our player 1, is going to pick action 1 by definition. So that means that whatever is here, whatever's selected by this minimizing agent has to be more than 8. So we know what's selected here between 11 and -2. We select 11 because it's our turn to make a decision, a maximizing agent. And over here, we select the maximum between X and -8. Let me format that a little better. And we're gonna, let's color this in just to make it nice and pretty. Okay. And that means that our minimizing agent at this layer is going to select the minimum between our left side, which is max x -8, and our right side, which is 11. And we know that this needs to be more than 8. So this right here needs to be more than 8 in order for our player 1 to be guaranteed to go down the left branch. Well, we know that 11 is more than 8. So if we ever pick 11, then we already satisfy the requirement. So that means that the minimum between max x -8 and 11 is unnecessary. This is the only variable where we might not be greater than 8. Well, we know that if we choose -8, so if x is less than -8 and -8 is our max, that we won't satisfy the requirements. So that's also moot. So it doesn't matter if we don't choose x over -8. -8 is definitely going to fail the requirement. So we simplify out the max function and we end up with just x is more than 8. This is our answer right here. If x is more than 8, then that means that this guy is going to choose x to maximize, and this guy is going to choose at least something that is more than 8 to guarantee that player 1 goes down the action 1 route. Alpha beta pruning. So alpha beta pruning is basically Minimax with a little logical optimization. We'll explain how it works by actually doing the problem. So to start, let's go into these text boxes. To start, let's just do a simple Minimax. Here's a minimizing agent at A, and we're going to select the minimum between 8, 4, and 9. Here we have 4 is less than 8 and 9, so we have A equals to 11. Let's see what happens at B. So at B, actually, let's take a step back for a sec. The way that alpha beta pruning works, we know that the parent node is a maximizing agent, and this layer, ABC, are all minimizing agents. I don't know why it says 11. So if B or C are less than 4, then D is going to go down A. We don't even care about B and C if they're less than 4, because D is always going to choose A. We already know that this is the maximum so far. What that means that as we continue searching through our decision tree from left to right, we're going to go to 3. And we know that B is going to choose 3 unless there's something low over here. In other words, by the time we hit this node, we know that B is going to be less than or equal to 3. It can't be more than 3 because this is a minimizing agent, and it's going to select 3 unless there's something lower. If nothing can be more than 3, that's already less than 4. So we know that D is never going to go down this branch, and we can prune it. By pruning, I mean we don't have to search anything else inside this entire tree. Inside this entire branch now. 5 and 6 are relevant. We don't even have to look at them because we know that they can't cause D to choose the B branch. Let's go to C. Go left to right. 7, 2. 2 is less than our current maximum between A, B, C. So we know that C cannot be more than 2. It has to be less than or equal to 2. And we don't care about anything else because no matter what, C is going to pick something lower than or equal to 2. and that's not going to change the decision. So enter the value of A, B, C, and D. Here it says when you prune on conditions, V is more than beta or V is less than alpha, assume that the value of the node is VV. I don't know exactly what that means, but I did check the solutions for this handout, and it's basically saying we're filling in the node that it optimized on. So A is 4, of course. B is going to be 3 because that's the node that we stopped on. We never looked at 5 or 6. And C is going to be 2. Even though this is a minimizing agent and there's a node that's less, we never even look at that. So C is 2. Finally, D selects the greatest out of these, which is 4. Which nodes are visited and not visited? Let's see. 5 and 6 are not visited. And then we have 1 over here that's not visited. And the rest are all visited by default because they were not pruned. Boom. What are some evaluation functions that could be used to limit depth of a tic-tac-toe search tree? With chess, there's evaluations such as like center control of the board, the value of various pieces. One evaluation function we can use, those evaluations in chess were created based on how people think about the game. Like when I play chess, I want to have center control. I want to not lose all my pieces. Like my pawn is worth something and my knight is worth more than that pawn. I make those calculations as a human, and I'm encoding them into an evaluation. Tic-tac-toe has very similar things. I value the center most of all. So I'd say the center, my heuristic is going to be as follows. If I control the center, then I'm going to have +3. If I control an edge, then I have +2. And if I control a corner, that's kind of neutral, so it's whatever. If I have 3 in a row, that was winning the game, so that's plus infinity. And we can just reverse this for the enemy, for the adversary. So this is my heuristic function. It's if I control 3 in a row, then I win and I have infinity. So I'm definitely going to go down that path because that maximizes my reward. If I control center, that's +3. So I'm going to try to control the center. And if I control an edge, that's +2. So anytime I look at a tic-tac-toe state, I'm going to run these really easy to check functions and create a heuristic, an evaluation from that. Thanks for watching. Good luck in class. Bye.